Hello everybody, my name is Seth Croslow. I'm a rising junior at Monmouth College in Monmouth, Illinois, where I'm studying chemistry and physics. For the last summer, I've been a professor of Dunaway Wong's group, where I've been studying intermediates in the water oxidation pathway. So water oxidation is one part of a larger reaction of water splitting, which consists of breaking the bonds of water and forming oxygen and hydrogen. So water oxidation focuses on the oxygen evolution part. And so for us, we're doing this by using a catalyst to facilitate this oxygen evolution. So we chose a cobalt catalyst to do this, and so this graph shows you the overpotential, or how much extra energy you have to put in for oxygen to be produced for several catalysts. And so ours is around the middle, but we chose to study this because cobalt is very prevalent within the Earth, and it's also been heavily studied in the literature. And so we're focused primarily on the oxygen-oxygen bond forming step and the intermediates within that step. And so we're studying those using various electrochemical methods and FTIR, which I'll get more onto later. So this pathway shows the overall reaction for oxygen evolution on our catalyst, starting over here. And so you can see at about 3 o'clock you have 2 steps going to about 9, which are just a series of proton-coupled electron transfers. And so we're actually focused on this step right here where the oxygen-oxygen bond is formed. And so currently there's 2 proposed mechanisms by which this step occurs. The first is an intramolecular oxygen coupling reaction, where these 2 oxyl radicals bridge together to form the superoxide intermediate. The second is a water-hydrogen atom abstraction, where water attacks the oxyl radical and forms this peroxide intermediate. And so one key difference between these 2 intermediates is that the second one has hydrogen, or has water. And so this is where we decided to start our study. So we utilize a water and salt method. And so by adding salt into water, you create this solvation sheath, which kind of traps water molecules around the cation of your salt. And so this lowers the water activity. And so the more salt you add, the lower water's activity. And so this graph shows you 4 different water activities, plotted against current density, which is how many electrons flow throughout the system, and therefore how much oxygen is being produced, versus potential. And so we hold a constant potential and measure the current density. And so you can see at lower potentials, all of the water activities have about the same current density, which indicates that water isn't playing a very large role within the mechanism. However, as you increase the potential, you see they start to spread out, which means the water is playing a role. So this led our group to believe that there's actually a mechanism switch from the intramolecular oxygen coupling at lower potentials, switching to the water-hydrogen atom abstraction at the higher potentials. And so to validate this, we decided to focus on these intermediates and do some FTIR studies. And so FTIR stands for Fourier Transform Infrared Spectroscopy, and this is a simple diagram of how it works. So we have an IR source that goes between a series of mirrors to change the intensity of light. This then goes through our sample here, which absorbs some of that light. And so that absorption is determined by the mass of the atoms within your sample and the strength of the bonds. And so we're looking at trying to distinguish between this peroxide and superoxide intermediate. And so the literature tells us that these 2 values are about where we should expect to see our intermediates. And so since we mentioned before that this is a potential dependent switch probably, we decided to collect FTIR data at various potentials. And so we start around this 1.8, we hold that potential, and then we lower down and then cycle back up. And so each of these lines will correspond to a line on the FTIR in the next few slides. So we started out using this auto configuration, which uses a zinc selenide crystal. And what we do is we deposit our catalyst onto an FTO-coated glass electrode and then place it face down onto the zinc selenide crystal. We then add our electrolyte into that. However, we noticed a large background interference with this, and also the oxygen that's being evolved got trapped within these 2 layers, which made some more interference. So we switched to the Kretschmann configuration, which uses a silicon ATR wafer that we directly deposit our catalyst onto. And this had a smaller background interference and allowed the oxygen to just travel up into the solution. So you can see here, this is our FTIR data showing wave number, or the frequency of IR light, versus absorbance. And so each of these lines represents a specific potential from that graph that I showed earlier. starting at 1.8, going up to 1, and then back up to 1.8. And so you can see here around this 1014 wave number, we have a small peak right here. It's very hard to tell because we have this interference from phosphate from our electrolyte here. But we believe this to be one of our intermediate species, and you can see at the higher potentials it's present, but as we decrease the potential, it decreases, and it's also reversible, as you can see it back up here. We also notice a second intermediate possibly down here. However, there's no presence as we increase the potential again, so this may just be some kind of noise and possibly not an intermediate. So we then switch to a D2O electrolyte solution to see how our intermediates would change, and therefore the peaks would change. And so we can see this peak at 1014 did not shift, which indicates there's most likely not a proton within our intermediate. And then the peak at around 820, kind of hard to tell if it's just background or if there's actually a peak there, so we just kind of chose to ignore it for now. And then we did it in oxygen 18 labeled water, and so you can see here there's a shift to about 966 for that peak, for that intermediate, showing that it is an intermediate and not just kind of some remnants from that phosphate band interference. And so to further validate this, we decided to do another trial in a potassium chloride electrolyte solution instead of the phosphate to remove that phosphate band interference. And that's shown in this blue line here. And there's a clearly defined peak at the 1014 wave number, proving that it is an intermediate and not just some part of the phosphate band. So then we tried to recreate that electrochemical data that we had previously that led us to this hypothesis for a mechanism switch. And so we have a 0 molar salt and a 7 molar salt. And so the 7 molar salt will have a reduced water activity. And so you can see here this blue line with no water kind of has a shoulder at the peak that we're looking at. However, in further scans, this peak became removed from the actual scans. And so this could be indicative that it's not actually changing. So we'll need some more data collection to actually validate that. So in summary, the steady state measurements that we collected had an increased dependence on water as the potential increased, which led us to propose this mechanism switch. And for the FTIR data, that superoxide intermediate was present at high potentials, and we currently don't know if there's any presence of that peroxide intermediate. And from the water and salt data, we can see that that peak at 1014 could possibly be reduced with water activity in the earlier scans. However, at the future scans, it seems to be diminished. And so currently the FTIR data doesn't really prove or disprove our mechanism switch hypothesis. We'll need more data to determine that. And so for future plans, we'd like to use electrochemical quartz crystal microbalance. And so this will allow us to see the mass change of our film and see if we can actually quantify water's absorption onto our catalyst at higher potentials. And we'd also like to do some additional water and salt experiments in FTIR and try to reduce the effects of that phosphate band. I'd like to thank Cha Lang for being my mentor and helping me throughout this process, Jeannie Lee for doing all of the FTIR and with that, and Dr. Dunway Wong for being my PI and giving this experience, as well as the Boston College Art.
Have y'all thought about using a 50% mixture of O18 and O16 water? So you might be able to see 3 peaks in that case.
So I feel like if we actually did that, since our peak is so small to begin with, we'd have a reduced intensity for the peaks since there would be 2 of them instead of 1. And so I feel like if we did that, it'd be pretty hard to determine if we could actually see the 2 peaks and not just incorporate that into the background. But it could be something we could look into.
Other questions? And just one. The experiment is done in an electrolyte, or it's just
Yes.
water?
Electrolyte.
So have you checked like the effect of the electrolyte, or?
What do you mean?
Well, maybe like a different electrolyte.
I don't think we've changed the electrolyte. So we need the electrolyte to be a proton donor for the catalyst. So we could probably change the electrolyte, and that could be something we could look for.